Okay, let's be clear about what Kepler's second law actually says. So I've drawn a diagram here with the sun and a planet here. Let's call it planet Q. And let's draw some arbitrary orbital path. And let's imagine now that planet Q in 1 week's time travels to, let's say, here. Now the area swept out is this area here. Now let's imagine planet Q somewhere else, let's say over here, and in 1 week's time it goes to here. Now the area swept out is this area here. And if we call the area swept out delta A, and we divide that by a time interval, delta t, in this case delta t equals 1 week, what we're saying is that delta A divided by delta t is some constant. Let's call it k. Now we can imagine shrinking down the time interval to a smaller and smaller value. So let's say now Q is here, and in 1 day's time it travels here. So now the area swept out is smaller. However, delta A over delta t still equals a constant k. In this case, delta t equals 1 day. Now, Newton had a concept of infinitesimals and limits, and he might say that we could shrink delta t down to some arbitrarily small value or time interval, and we could call that delta t. We're using the lowercase delta, and the area swept out would likewise be a very tiny area, which we would call delta A in that manner, but it would still equal the constant k. And then in modern terminology, we would say as delta t approaches 0, dA over dt still equals k. And so this will be a modern shorthand way of stating Kepler's second law. Let's imagine a planet, Q, traveling through our solar system. For our thought experiment, gravity has been turned off for the time being. At noon, planet Q finds itself at position A. Planet Q is traveling with velocity v such that after 1 hour it arrives at position B. Note that I am going to scale all velocity vectors so that the length in the diagram matches that of the distance traveled during an interval of 1 hour. This will allow us visually to equate velocity vectors with their corresponding displacement vectors as we think about the issue at hand. In accordance with Newton's law of inertia, there being no external forces at play, Q continues at constant velocity and after 1 more hour arrives at position C. Because Q's velocity is constant, the distance traveled over a 1 hour time interval is also a constant, and so the distance from A to B is the same as the distance from B to C. We can construct 2 triangles as shown here. Let's name them Virgo and Taurus. Question: is the area of Virgo equal to the area of Taurus? Notice that they share one side, shown in magenta here, which we hereby establish as the base of both Virgo and Taurus. Here I have drawn in the altitudes for the two triangles. First, we can show that triangles 1 and 2, shown here, are congruent. Remember that the distances from A to B and from B to C are equal. The angles shown here in orange are equal because they are opposite angles of intersecting lines. Triangles 1 and 2 each have one right angle, so their third angles must be equal as well. Triangles 1 and 2 are therefore congruent based on the side angle rule. So we conclude that their altitudes must be equal. By extension, the altitudes of triangles Virgo and Taurus must also be equal. Moreover, since these triangles share a common base, their areas must be equal. So planet Q, with gravity turned off, is sweeping out equal areas in equal times. Now let's go back in time to the point when Q is at position B, and let's turn gravity on for a brief instant. Or, as Newton put it, let it be attracted towards the center S by one impulse or impression of force. An impulse is a vector, and it is defined as F times delta t. Here Newton specified that delta t was to be considered very small, and so I have used the lowercase Greek letter to represent delta. An impulse produces a change in momentum, delta p. We take the mass to be constant, so the impulse produces a proportional change in velocity, delta v. Recall that all velocity vectors are scaled so that their length in the diagrams matches that of the displacement of q that would occur over 1 hour's time. Therefore, as planet Q travels on from point B, its path is influenced by two velocity vectors, v and delta v, so that we must add these two vectors to produce a resultant vector, which we will call v prime, and we will use v prime to plot Q's course over the next 1 hour. To perform this addition, we make an exact copy of delta v and place its tail at point C. The resultant, v prime, brings Q to point C prime at exactly 2 p.m. This forms a third triangle, which we will call Pisces. Let's compare the areas of Taurus and Pisces. I have drawn in their altitudes. Notice that delta v is parallel to their common base. Therefore, the altitudes are equal, and because they share the same base, the areas of Taurus and Pisces are equal. We have shown, therefore, that the areas of all three triangles must be equal. So, even though gravity deflected the path of Q, the areas of Virgo and Pisces are equal. Now that we have shown that the areas of both triangles are the same, we can define those areas in a standardized way. First, we define the angle of azimuth, theta, with reference to a ray extending horizontally to the right. Next, we assign an angle alpha to each velocity vector. For example, I am showing here alpha for Q's velocity vector from B to C. We recognize now in explicit terms something that has been implicit all along, namely that the length of BC equals V times delta T. Finally, we define angle phi as being equal to alpha minus theta. With this definition of phi in mind, we go back and look at both triangles. We can see that the area in each case equals 1/2 times d times v times delta t times sine phi. One can easily imagine repeating this process over and over again to produce a complete orbital path, just as Newton did. Here is a sketch from his notebooks. Recall that we started with a time interval of 1 hour. Newton argues that if you shrink delta t down, down, down to what we would call dt, so that the increments of orbit are infinitesimally small, and you leave gravity turned on continuously, what started as an approximation becomes an accurate description of the relationship between a given time interval and the area swept out during that interval. We still have no sense of the size or the shape of the orbit, but we have proven Kepler's second law. Finally, note that if the formula for area holds true as we shrink delta t down to dt, then we can express the instantaneous rate at which area is swept out, dA over dt, in terms of d, v, and phi, as shown in this slide. Let's take a look at this numerator here because it is very closely related to the formula for angular momentum, which is conventionally designated with a capital L. And you might recall from physics that it equals mass times velocity times radius times sine phi, where phi is defined just as we've defined it here, or writing in our current notation, we might say m times d instead of r, absolute value of the velocity, times sine phi. Now, because the mass of the planet is so small in comparison to the mass of the sun, it doesn't have any significant influence on the orbital path. And furthermore, we can divide both sides of this equation by m, and we wind up with L over m equals d times the absolute value of the velocity times sine phi, which is our numerator. And furthermore, this value is often given the name specific angular momentum, L divided by m, and we can designate it with the letter h. So what we've shown here is that dA over dt equals h over 2. And this will be a very important formula as we proceed through the entire set of proofs. So Kepler's second law is equivalent to the law of the conservation of angular momentum. Angular momentum is conserved as long as the only force acting on the moving body is a central force. For example, as in this case, the gravitational force of the sun. In summary, dA over dt is a constant and that constant equals h over 2, where h is the specific angular momentum, which is conserved for any given planet orbiting the sun, and therefore h is a constant. And this leads us to one important point, and that is for any planet orbiting the sun, regardless of what the orbital path looked like, there would be a certain total area encompassed by the orbit, and let's call that A sub t for total area. And we could divide that by the period, theoretically, and that would also equal dA dt. Or in other words, this might be a way of finding the period of the orbit, because t equals a t over dA dt equals 2 times a t over h.